You are protected through the powers of cryptography. Every day as we use technology like our phones and the internet, the security algorithms that protect you are heavily rooted in cryptography. There's a lot of ways to do this. You may have heard about SHA-256, which is a cryptographic secure hashing algorithm that allows us to verify data on the internet. And there's a lot of options. This technique has evolved over the years, and there are many varieties of algorithms that allow various levels of security to be implemented. As the power of compute evolves, many of these older algorithms are outdated and can now easily be broken. So we need to make sure that we are using algorithms that are secure and safe even from brute force. We see there's a new algorithm here. Well, actually, it's not that new, but it's BLAKE3, cryptographic hash function that is faster than MD5, and well, yeah. When you're comparing it to these older algorithms that are generally less secure, though it is still a feat to be able to be faster than any of the existing cryptographic hashing algorithms. BLAKE3 is a cryptographic hashing algorithm that brings with it several advantages over other cryptographic hashing algorithms. There are several important aspects when we are looking at a cryptographic hashing algorithm, such as most important its level of security, right? Can we easily crack it? Is it brute forceable? That would be bad. How much compute does it take in order to generate a hash based on the data volume that it's currently looking at? And then we compare those things against the existing algorithms to see how it performs. One thing I immediately looked for when looking at BLAKE3 is the rate of collisions. When data like an email or password is needed to be stored in a system, typically instead of storing the actual raw text of the password itself, we will cryptographically sign it in a way that allows us to store it in a database which represents a signature, essentially preventing anyone else from using that password in any other way. Even the folks who write that data to the database won't know what the password is. And that's why it's so critical. No one has the password except for you. And when it comes to collisions, you don't want someone else's password, even though it's different, right? Someone else's password is here, and then your password is right here, right? So it's like apple and orange. A cryptographic function take either of those and output the same result, and that is a collision. Which is bad because that means that the attack space for your password could be extended to use, orange, even though you wrote apple as your password. And while looking at in here, I didn't see anything about collisions. Obviously, that's a big part of the level of security and validation of how secure it is. However, we'll go through with what exactly is mentioned here anyway to see how we will find situations that we can detect. Maybe it's better to use a BLAKE3 compared to a SHA-256. Cryptographic hash functions are used very frequently to protect identities and our access to systems. That technology happens to be a foundation of cryptocurrencies, which brings with it a stigma. We see all these cryptocurrencies and the challenges that come along with the Wild West of data exchange, which represents currency. This is unfortunately attached to cryptography and crypto and the biases that come with it. Taking a look at BLAKE3, there's a chart here that describes the performance capabilities of the number of hashes that we can get using BLAKE3 algorithm compared to the others here listed. And it's actually a surprise. Look, SHA-512 is actually a little bit faster than SHA-256. Is it really that bad? Like, why not take advantage? I mean, it is a longer output, right? So you have to store more data, and that is a trade-off. But as they're claiming, which is extra interesting, that BLAKE3 is as strong or stronger than SHA-256 in terms of security perspective, and yet it is enormously faster. We see here that SHA-256 was based on SHA-1, which is weak, which is not good. We want strong security. BLAKE was based on Cha-Cha-20, which was based on Salsa-20. Those are fun names. Great names. These are both strong cryptographically. There is a concerning paragraph here that I'm interested in diving real quick. It says the NSA is signaling a lack of confidence in SHA-256. Okay, so they say here the signal is about a hasty SHA-3 contest after Wang broke SHA-1, which, that's a problem. And the theme of the contest was don't be like SHA-256. Yeah, that counts as a signal. I definitely say that is a strong signal. Oh wait, this is an even stronger signal. They banned SHA-256 from being implemented in new designs used by the US government. Wait, really? All right, they link a PDF here. Let's check this out. I did look. there's a section here that says, what is the Commercial National Security Algorithm Suite 2.0? Series of algorithms approved for eventual use. Well, I see things like SHA in here, which mentions 384 or 512, and then it looks like some sort of adaptation of SHA-256. So there isn't really an immediate obvious, like, hey, there's a list of unapproved crypto hash functions. That's not, I don't see that here. However, they are signaling here that they do want us to continue using 384 and 512. So yeah, I guess based on this document, it says SHA-384 remains approved in the newest suite here. The NSA believes this provides sufficient security. Though looking back at the chart, they do say SHA-512 is more interesting from a performance perspective, because we saw here that SHA-512 is looks like really close to all pretty, what is that? Not quite 2 times faster, but a little bit better. So really in this case, we're comparing SHA-512 to BLAKE3, which is still is a lot faster. BLAKE3 versus SHA-256, we're going to take a quick look at reasons why we want to take the advantage of BLAKE3 and why we might want to prefer BLAKE3 over SHA-256. We see here that Zuko describes some details. So SHA-256 was designed by the NSA, while Blake, the original, and BLAKE3 were designed by John Felipe and others, including Zuko. John Felipe and the other contributors did a lot more of the cryptographic heavy lifting. So we're seeing signals that SHA-256 is being repeatedly signaling a lack of confidence, but through the NSA and other organizations. And going forward, new designs to be used by the USA government should most likely not use SHA-256. Now this is concerning because in many existing big cloud vendor providers, they do provide majority of their API access through cryptographic signatures that leverage SHA-256. One of the advantages though, they do allow you to change and choose which cryptographic signature method you're using, so you can immediately have an upgrade path to using SHA-512. What's great to see here is that during the SHA-3 competition, that Blake exceeded even of Kekak, the final SHA-3 winner. So wait, so Blake didn't win? Okay, so it looks like Kekak, is it, how do you say it? Kekak, okay. That Kekak was the winner. However, there's a little bit of explanation here that there was more crypto analysis depth applied to Blake. So it's kind of hinting that Kekak got a little more pass. Okay, I was looking for this. So things like collision rates and feasible attacks and vulnerabilities. Known feasibility attacks can break 31 out of 64 rounds of SHA-256, which is almost half. Compare that to known feasibility attacks can break 2 out of 7 using BLAKE3. Okay, which is a 20% improvement. It looks like BLAKE3 is showing up to be a powerful cryptographic hash function. Comparing that to SHA-256, we're taking a look at some reasons why we would choose to prefer BLAKE3 over SHA-256. So we were looking at earlier why it's a lot faster compared to SHA-256, and we're also seeing signals that the NSA is recommending using other algorithms beyond the SHA-256. There's a nice little bonus with BLAKE3. Out of the box comes a security feature that can protect users for common use cases such as length extension attacks and standard method of key personalization tags, which allows and guarantees domain separation. With those kind of features, it looks like we are extending the footprint of the total coverage of advanced security, which reduces the entry point for possible vulnerabilities. We're also seeing, check this out, BLAKE3 also comes with a performance competitive against the SHA-256 in cases where it's sometimes more efficient, even when your CPU comes with built-in acceleration circuits. How did they do that? Oh, maybe it comes in play with, oh wait, and it does talk about, is it say, wait, hold on a second. It doesn't mention technically here, based on this next mention, that it provides parallelizable performance advantages, which basically means that, okay, so I'm thinking that because it can be parallelized across multiple cores, multiple threads, this allows BLAKE3 to, extend its capabilities to be even that much more efficient. So when we are signing or hashing big data, gigabytes and gigabytes, that's a lot of data. The major benefit with BLAKE3 is that it can split that workload across multiple cores and threads, where SHA-256 requires it to take a lot longer because it is not parallelizable. And a second performance gain power, here we see that it's less widely understood that inside a single compute device, new tech improvements provide more and more parallel power. FPGAs and GPUs, and it is true in CPUs because of vectorization upgrades. With FPGAs and GPUs, it allows you to run operations in parallel, such as a math equation that does some work here, maybe some addition, multiplication. And there are a lot more cores in a GPU and an FPGA, right? Like thousands of cores, tens of thousands of cores. Comparing that to a CPU, which, can go up to hundreds of cores. So that's a much bigger difference. Let's try out BLAKE3 and see a quick little comparison with SHA-256. We'll try it out right now on our computer using the GitHub information provided. We see that the official Rust and C implementations of the BLAKE3 cryptographic function here is available to us. So we see that it is a lot more performant, more powerful, comparing it to other hash functions that we are actively familiar with. Okay, we're taking a look here that says it compares the C implementation with the Rust implementation, that we would prefer to use the Rust implementation because unlike the Rust implementation, the C implementation is not currently multi-threaded. So let's give it a try out. We're gonna copy the install. We're gonna use the command line tool. Then we're gonna install B3sum. Let's see what this does. It'll take a little while here. All right, we've got it installed on our system here. B3sum, see what that does. If it does any, probably expect some input. Okay, I see here. So we've got a nice little helpful output when it will hash a file, and then when no file is given, it's looking for standard input. All right, let's try standard input real quick. So echo some test data here, pipe that into B3sum, see what it does. Oh, there we go. We got ourselves a nice little hex encoded hash. So this is what it looks like when you type in your password and send it to a system that'll take your password. So for example, my super secure password. That string will get sent to something like a B3sum or SHA-256. Instead of storing the password, it stores a signature of the password. And this is powerful because now when this is stored, if somebody ends up reading that, they won't actually be able to determine what your original password was. So now we can compare that with the standard SHA-256 with OpenSSL SHA-256. And there we go, there's the output. Actually, it's interesting to see the length is the same, being that it's a different algorithm altogether. We're going to see a different output result. So we can run a quick little non-scientific test to see what the difference is comparing the two. In terms of speed and performance, we see time on the B3sum and then OpenSSL 256. So I ran these a few times and I noticed that B3sum allowed, with these numbers, basically we're seeing that they're about the same-ish. In the case where it's a small input, roughly the same. So what I want to do next is test a larger amount of data. What we can do is take a look at sending it a whole bunch of just, large chunks of data to B3sum. Let's see what that did. What, that came back really fast. Okay, so we're looking at around 66 milliseconds, and that's for 1 megabyte of, 100 megabytes of data. 100 megabytes of zeros. And then we will do 100 megabytes of zeros for OpenSSL SHA-256. Let's see what that does. Okay, it did. Oh, okay, it did. Okay, see here. Okay, so we did take a lot longer with 100 megabytes. With 100 megabytes, we're looking at roughly 5 times slower. Wait, or is it a lot more? Yeah, okay, so OpenSSL SHA-256 looks like it took just under half a second here, comparing that with B3sum, which took around 40 milliseconds, which is significantly different. So if we need to cryptographically sign large chunks of data, B3sum is going to be our friend, BLAKE3. I can also imagine if we're doing a lot, even if they're small chunks of information that we need to cryptographically hash, but we do a lot of them, BLAKE3 is probably still going to come ahead because that allows us to do a lot more. So we would need to test that out. Even though just looking at here the CPU time, for example, compared with OpenSSL SHA-256, we see that the BLAKE3 uses less CPU overall. Depending on your use case, you might as well benchmark and see which one is better for your situation. You might see that BLAKE3 ends up being that much better for your use case. Increased security, increased performance, lower cost of operation, win all over the place.